Good afternoon, everyone. Welcome to this webinar organized by the Network for Heating and Cooling with the name of Achieving Net Zero. We have two talks today. As you may know, this network is funded by EPSRC with a view of finding the ways of addressing some great challenges in decarbonizing the whole operation of our society and our industry. And again, the heating and cooling in the summer time is a big consumer of energy. So I hope that you will find that the talks today give you some idea of challenges and some idea of the technical approaches that we may have. So I thank you all for the interest in this area. All this said, I would like to present you our first presenter, Dr. Yousaf Khalid, who works at Durham University. He came there from Chester last year. He's an expert in building modeling. He works extensively in sustainable energy systems, and he will present his recent research, which is, as far as I understand, endorsed by the Church of England with the topic of net zero for heritage buildings. So, Dr. Khalid, may you begin your presentation?
Okay, thank you, everyone. Thank you for inviting me to present this project, and thank you for the introduction. So let's start. So this project is funded by EPSRC and Durham University, and Church of England and Renewable Energy Network are part of the project, but it's funded by Durham and EPSRC. And apart from that, there's three churches and in Durham, as well as Durham Cathedral, who are part of project. So a bit of a background really in terms of historic buildings. So Church of England has decided to decarbonize the buildings by 2030, and it has thousands of buildings, listed buildings with lots of carbon emissions. And so this project came about to look at some of the case studies and see what options we have for net zero in terms of this category of buildings having very different fabric and heating requirements and occupancy patterns compared to our normal commercial or domestic buildings. So the project basically goes through 4 stages, really. It went through data gathering exercise, trying to conduct basically an energy audit, collecting all the information that was needed for modeling, as well as instrumenting the buildings to collect some monitored data. We then went on to create some baseline models of the buildings involved in the project, and then calibrated those with utility bills, and eventually then introduced some net zero interventions and then assessed their impact on decarbonizations to create some pathways for different church types towards decarbonization. So there are a couple of buildings that are in this project. So one of them is St. Brandan's Church, located outside Durham in a small village. And it's surrounded by a castle and trees and lots of land, as well as golf course. Has 2 gas boilers, underfloor heating, trench heating, as well as radiators. So this is more of the modern church compared to the other ones, because it's been renovated in the past few years, as it had a big fire in it. So it's got insulated roof, LED lighting, although still obviously stone walls, thick stone walls and single glazed windows. So this particular church is a low occupancy, 2 hours per week on Sundays, but it has a high, heating period. You have to run the underfloor heating for a while, 19 hours. So it starts off around Saturday to try and bring the temperature up to a comfortable level around 17, 18 degrees for the times that it's opened on Sundays. So it has electricity demand of 90 megawatt hours in terms of gas and a small electricity demand. So overall, around 17, 18 tons of emissions per year. Again, another church that's involved, a little bit bigger church, 25 hours per week of occupancy, 13 hours of heating. Again, it has 2 large gas boilers, underfloor heating, thermostatic controls, as well as radiators. So underfloor heating and radiators both. Doesn't have LED or insulated roof. And this is located in the city center of Durham. We also have St. John's Church, which is it is a medium-sized church, but it has high occupancy periods, 24 hours per week, lots of heating hours as well going in. It has 2 parts, so it has solar panels as well as 2 gas boilers covering the church as well as the other part of the building, which contains kitchen, foyer, as well as activity rooms. This one has LED lighting, insulated roof, as well as a PV system. So part of it is double glazed, part of it isn't. So the church side isn't double glazed. The other part of it, the extension, is double glazed. So these were the 3 churches. So this is located just outside city center, so suburban area. It has some land next to it, and it has got some 17 panels, PV panels installed. And lastly, we have Durham Cathedral. That's part of the project, and that's a lot bigger. Durham Cathedral, it has 7 control zones. So it has about 7 200 kilowatt gas boilers feeding into its 7 control heating zone circuits. So it's got underfloor circuits like shown with the red lines, as well as radiator circuits, which are in the triforium level, higher up, heating the triforium galleries, whereas the underfloor are located in the aisles and the transepts along the building. So there's 7 circuits heating different parts of the cathedral. At the moment, they are currently installing LED, but it's still uninsulated roof. It does have air conditioning as well as natural ventilation, but air conditioning is also at each corner of the cathedral. So single glazed windows and really thick stone walls. It has a lot, 40 hours of occupancy, 60 hours of heating per week going into it. So we then started with doing 3D models of these buildings. So we created 3D models. We went through the buildings, measured up all the dimensions, as well as got some architectural drawings, floor plans, etc., wall build-ups, floor build-ups, etc., whatever we could get. And we used that to create 3D models, including as accurate as we could of the windows as well as doors, etc. So this was done for all 3 buildings, St. John as well as the cathedral. And that took quite significant time to create these 3D models. Once these were done, we then started adding all the data to carry out the dynamic simulation for the whole year to do energy assessment, carbon emissions, and costing. This has involved basically putting in, building fabric information, such as you can put in the different material layers for walls, floors, and roof, or calculate the U values, etc. So all that information is fed in, including material layers of these different parts of the fabric, also including dynamic weather conditions, so dynamic outside temperature data, solar, wind, heating systems. So there are heating system models that are defined in the software, which are based on real data from National Calculation Methodology for the Part L building regulations in the UK. So these were used as part of the simulation. We also had temperature set points as well as profiles that were defined for scheduling the heating systems, as well as ventilation. So ventilation, for example, air change rates were scheduled, lighting, turning on and off lighting every day, as well as occupancy coming in and out. So daily, weekly profiles were generated, and then these were used to create the whole year's profile of the building, of how it operates. We also included internal load, so lighting was defined, and then how many lighting units in each part of the building, and how and what their watts, what they were consuming, and how that's related to the heat output that goes into the building from the different lighting units. So internal heating loads, as well as from people, were defined. We also defined PV, so you could add solar panels in the case of St. John's, as well as wind turbines you can add as well, but that wasn't in the baseline buildings. You defined radiant fraction, so for underfloor heating, how much of it is radiant, how much of it is convective. Sensor setting, so what you're actually measuring in the building. So dry bulb temperature was measured, because these are thermostats, not comfort temperature measurers. Ventilation, air change rates, fuel tariffs, and carbon intensity. So carbon intensity, carbon factors were taken from base data. The church provided the fuel tariffs that they were currently on. So this was all done in a software called IES. IES Virtual Environment, the company's integrated environmental solutions. So this was the software that was used. We then calibrated these baseline models. So once all this data was put in and attached to the 3D models, we then ran the simulations for the whole year for each of the 4 buildings. And then we calibrated, and then we basically, the baseline was calibrated to the bill data, quarterly billing data for each building. So these graphs are showing the 4 buildings, their gas and electricity calibrations. Because we had modeled these buildings and scheduled them as they're operating now, we didn't have the billing data currently, but we had billing data from the past. So we, to show that there's confidence in these models in terms of predicting realistic gas and electricity consumptions, we compared them to the past billing data. So in this case, the orange line is the model line, the models that predicted the gas and electricity consumption, whereas the other lines are the real bill data. So obviously there's some differences, because obviously the COVID part of it has some impact there, because prior to COVID, the buildings were operated in a different manner, whereas now they are operated differently. And so the orange line, the model predictions are not as matching with the previous year's billing data. They're obviously within the band of that you would call reasonable, because that's where the previous results have been, previous billing data. So we are considering that it's predicting results which are credible, that they're quite close to what was in the past. So we can then look at from the simulation, for example, heat losses as well for the baseline building. So external walls, windows, and ventilation. So gray part is external walls, orange is ventilation, blue is windows, yellow is roof, light blue is ground floor. So heat loss is going through them. And there's obviously, these are dominated by the natural ventilation as well as external walls and windows. But there's differences with roof based on which buildings are insulated. So obviously St. Brandon's roof is 5% heat loss because it's well insulated. So is St. John's, whereas Cathedral has a lower heat loss compared to St. Nicholas, because the Cathedral has obviously triforium levels, which obviously delay the heat loss. Triforium levels sort of disconnect the roof from the main heating spaces. Ground floor, there's some differences because some buildings had carpets, whereas others didn't. Again, roofs, depending on which had insulation. Drafts are quite small, mainly because there's obviously lobbies in the cathedral, as well as internal, external doors, which restrict drafts, as well as all the sheltering that was around these buildings. So St. Nicholas is right in the middle of city center. There's lots of buildings around it, sheltering it, whereas St. Brandon's is surrounded by large trees. St. John's is surrounded by buildings and trees as well, but not as much as the other ones. So we were carry on with in terms of interventions. So we looked at all these interventions. So we started off with demand reduction, looking at how much you would save if you reduce set point by 1 degree, switching to LED lighting, then start looking at fabric efficiency, insulated roof, secondary glazing, and then start to look at low zero carbon technologies such as solar panel, biomass, a hydrogen boiler, and then look at electrification of heat, so pew heating, radiant heating, direct electric boiler, and off-peak electric boiler and storage heaters, as well as heat pump configurations in terms of ground source heat pump, air to water, and ground to air, ground to water. So we looked at these interventions to see what was suitable for each building in relation to how it's operated. We did some solar analysis as well. So for when it came to looking at solar analysis, we did through the software, we looked at, you know, which pits of the roof are most exposed to solar throughout the year, and so accordingly we placed solar panels on the roofs to assess how much they generate for the building. So in terms of results, I'm just showing you these. These are so all the interventions individually we looked at for each building. So you start off by switching, your baseline gas boiler to how much you would reduce carbon, how much it would change carbon per year, operating cost change per year, above or below or in comparison to the baseline emissions and operating cost. So we then ranked them in terms of the individually interventions which would reduce or change the most carbon, reduce the most carbon. And we sort of shaded them in terms of green to red. And so obviously direct electric boiler actually didn't reduce carbon, but increased carbon. So did electric storage boiler. Direct electric boiler costed a lot more to run over the year. Operating cost was very high. As you can see, it's colored red in the middle column. Obviously, hydrogen boiler in the first column reduced the most amount of carbon, whereas same was the case with biomass or ground source heat pump. Electric storage heater on economy 7 reduced a lot more. And then apart from these 5, the other interventions such as radiant heaters, pew heaters, they did reduce carbon, but not as much. So you would need some offsetting. We then did some costing on capital cost on these interventions, but these don't include scaffolding costs. That's the only thing that doesn't include it. We did these individually, but ideally we want to do it cumulatively to see what kind of options we have in combination. So I'll just show you the results that I did in combination for each building. So for St. Brandon's, it's already an insulated roof LED. So we selected some interventions for heating systems and then added PV to them to see how best we can reduce carbon over the year. And we also looked at 2 cases, one for current year and one in future, say 2035, when the electricity grid would be a lot more decarbonized as predicted. So we used 2 different carbon intensities and looked at combination of interventions to see what would be ideal for the church. So these columns are showing you annual, not change, but annual CO2 for this year and for 2035, and annual operating cost currently. We don't have operating, obviously, tariffs are changing all the time, so we didn't really calculate costing for 2035. So in summary, if you add PV to majority of these different heater options, so pew heating, radiant heater, storage heater, heat pumps, biomass, hydrogen boiler, what you can see from the first column is is that biomass comes out as one of the options, as well as ground source heat pump, air source heat pump, ground to air and air to air. These are the ones that actually reduce the most carbon, and they reduce it to actually they start saving carbon as they are negative. They don't just reduce it, but they actually save more carbon. So annual costs in some cases were, for example, air source heat pump, they're higher than the baseline, which is right at the top in orange in the third column. Hydrogen boiler has a higher operating cost annually. And then the capital costs, obviously, for a biomass is very high. In comparison, hydrogen boiler is a lot cheaper. So we did these sort of options for each building. We did the same for St. Nicholas. We again did the same for St. John's. Again, we're getting the same sort of pattern where heat pumps, biomass, hydrogen are reducing carbon. Obviously, they have a higher capital costs, but pew heating, radiant heaters, they are there. They reduce carbon, but not as much because they're restricted by where you can install them. You need to offset by, buying carbon credits, for example. Generally, in this case, St. John's case, you do save a lot on operating cost. So almost 1,500 on average you are saving by switching to an electric heater, whether it's electric storage heater or installing PV with heat pumps. Same was done with Cathedral. So Cathedral, again, similar options were basically resulted in that it's better to install a heat pump or biomass or hydrogen boiler, or wait for hydrogen boiler. But obviously biomass is very high in capital costs. So in terms of comments, well, hydrogen option, not promoting hydrogen option so that everybody just waits for that and doesn't decarbonize now. Hydrogen option is for those, say, who have already installed a new heating system, and they can then, obviously, they can't rip that one out and install a more expensive, say, heat pump. So they'll have to obviously wait for a while until they recover costs from their investment in a gas heating system, and then wait, and maybe if hydrogen goes off and we actually have hydrogen boilers, then they can be installed. So that's an option for those who already have installed new heating systems. For those who have old heating systems, they can decarbonize now with, say, heat pumps. There's obviously trials going on, and there's a decision being taken place in the next few years, 2026, on hydrogen in terms of its implementation into the gas network, as well as there's trials going on with National Grid and all other heating manufacturers putting their hydrogen boilers. There's currently trials happening in the country. There's obviously concerns with biomass being a totally green solution. There's practical issues with it as well, and planning permissions considering the heritage building. So these are things to be considered and discussed with your DAC, Diocesan Advisory Committee, as well as discussing with building services. These are obviously, we've done a technical analysis, but there's a lot more issues relating to planning permission and practicalities that do need to be considered when you're going for these systems. It's not that we are proposing biomass or hydrogen, and all these options need to be carefully considered with your engineering consultants on a case-to-case basis for their feasibility. Again, solar and insulated roof, we considered insulating the whole roof and putting as much solar panels as possible based on the available roof. But that obviously is planning permission, I think, required in terms of how much you can put on. Embodied carbon was not considered, but it's something that we hope to include as part of further analysis. Finally, I think where the work is going is that we're going to have to translate this into a more simplified tool. So the results that we've got out of it in terms of energy consumption, gas and electricity, these can be converted into a more simplified tool for churches in which they can put in their electricity, gas tariffs for each different interventions, and then work out their own carbon emissions as energy prices change. Because this was done for the current billing information, but obviously these are very not predictable at the moment. So we're hoping to create a tool where the churches can put in their own information. This is something as further work. There's obviously validation needs to be done for the monitoring data that we are currently doing in the buildings. There's obviously the problem of energy tariff predictions. Where are energy prices going? Green tariffs is another area that needs to be considered, green electricity and gas. We haven't considered that in this analysis, but it needs to be, I think, looked a little bit deeper, because it's a different way of estimating carbon emissions compared to the normal way that in building regs is done through carbon intensity. And there's other areas to look at, like heating positions, so heated positions, for example, heated cushions or radiator positions or trench heating, where they're located will have a different impact on your comfort, thermal comfort. There's obviously dynamic carbon intensity that needs to be looked at, considering that we now have a more varied generation of electricity. So you have a lot of random generation of from solar and wind, and that obviously creates you can't really create and put in your calculations an average annual carbon intensity as is currently done and proposed by the government. You need to have a more dynamic carbon intensity to look at the performance of heating systems throughout the year. Air change rates, so pressure testing is something that would be good to do, as well as looking at setback heating in terms of fabric conservation and humidity. This is something that we hope to do. We're currently monitoring humidity levels in the building. So stratification and buoyancy effects, I think these can be looked in more detail using computational fluid dynamics modeling, something for future as well. So there's there's things that can be explored. It's a really active research area. I hope you liked the presentation. Sorry for going on a bit longer, but thank you for listening.